All right, topic 4, lesson 4 on glass. Rapid technological discoveries have been very evident in the manufacture and use of glass in electronic devices. Back in the day, glass was glass, and it was very brittle, it was cheap, but it was easy to break. Now, we've got all kinds of crazy high tech glass with electronics built into it, and it's super cool. Nature of design, different properties in glass for aesthetic and safety considerations. The future of glass is interactivity alongside electronic systems. So you can see some images I put in there. And the one on the right clearly has electronics built into it. Structure of glass. Its use is becoming increasingly prominent in building materials and structural applications. Back in the day, it was not used for used as a load-bearing material. Now we can start to see structures like the Louvre, which has a ton of glass on it, and it can bear some of the load. Characteristics of glass. It's got high transparency. Its color can be clear or it can be of some other desirable color. And its strength is getting better and better. The picture on the bottom left of the guy standing on the glass panel, we had our windows replaced in our house about 5 years ago. And the guy who came to do all the measurements was a pretty big guy, but he was willing to put down one of their windows on the ground and stand right on it. The guy must have weighed about 300 pounds. The window did not break. The glass that they are using is new technology. Couldn't do that 20 years ago. Applications for glass. IB wanted me to say that. So I found a couple pictures of different applications for glass. There's a nice little glass kayak, or canoe, I guess. And then a glass keyboard. That's kind of fun. Recovery and disposal of glass. Well, we can recover glass. And I'd say glass is one of the things that we're pretty good about recycling. The problem is when you recycle glass, it usually has to go in, it has to be used for a glass that's darker than the original. I think it's hard to make clear glass out of recycled material. But on the bottom right, you can see kind of the process they go through to recycle glass. 6, the earliest found glass was about 3rd millennium BC, which is before chickens. And so glass has been around for a long time. But up until about 150 years ago, it was considered a luxury item because it wasn't that easy to make. So you have to get it so hot to melt it down and then get it into your desirable shape. But our technology got better and better. And nowadays, glass is so cheap, you can buy a drink, a Coke or some kind of soda in a glass bottle, and the bottle itself costs just a few cents. Since then, glass has permeated and revolutionized many aspects of human life and culture, including arts, architecture, electronics, and communication technologies. If you've heard of fiberglass. All right, we've got 2 videos I'm going to show you, and they're both pretty good. They show you qualities of glass, but they're both interesting, so please watch them both.
Hey, it's me, Destin. Welcome back to Smarter Every Day. Have you ever been driving along and you suddenly stop and realize that you're moving around this world in a bubble of glass? It's kind of weird if you think about it, but it's really cool. Engineers have designed the glass in your car to be extremely safe so that when you have a wreck, you decrease the chance that you're going to get cut in half like the bad guy in Ghost. Remember the movie Ghost? Anyway, so today on Smarter Every Day, I want to investigate the 2 different types of glass that go into car windows. On the side, you have tempered glass, kind of like a Prince Rupert's drop, but flat. And on the windshield, you have annealed glass. First, let's talk about windshields. Glass on a windshield is designed to take a hit from a rock and not fall in on your lap. However, glass on the side windows are different. To demonstrate that, I got a window out of a car at a junkyard, and we're going to hit it and just watch what happens. Check out how it breaks. It doesn't break. That's because it's designed to be very, very strong in the center, but not on the edge. Watch what happens if we do the same thing on the edge. The whole thing shatters. To understand exactly why this happens, we're going to go to my driveway and use a high-speed camera to analyze this at 20,000 frames per second. What are you doing, Mr. Helper?
Holding glass.
He's holding the glass. This is not tempered glass. We've got a high-speed camera. This is a V1610, which at the time that we made this video is the fastest high-speed camera on the market. I have another helper over here. Not you. What are you doing?
Pushing the button when the camera breaks. I mean, when
The camera's not going to break.
the glass.
When the glass breaks. And what does that do?
Start the camera.
That's right. Okay. So what we're going to do is we're going to drop tempered glass and not tempered glass, and we're going to show the difference between the two, and there's a special announcement at the end of this. So let's do some science. You can move, buddy. I've got it. Yep, safety glasses on. You ready, little girl? Ready? 3, 2, 1. Okay, did you do it? Okay, you ready, buddy? Tempered. Are you ready? Do your best. 3, 2, 1. You get it? It didn't break. The tempered glass didn't break. Drop it from higher this time. Try to drop it on the corner too. 3, 2, 1. Yeah! It's not breaking. Okay, so it wasn't breaking, so we're going to take this wrench onto the bottom of the glass. And the idea is that maybe the wrench will actually twist that edge and break the glass when it impacts. We'll see. Hopefully it works. 3, 2, 1. There we go. Okay, this is the aftermath. You can see on the left we have tempered glass. On the right, that's just normal annealed glass. So the question is, why do they break differently? It's pretty awesome though, isn't it? Okay, so what did we learn from this experiment? Annealed glass is just normal glass that's been heated up in the manufacturing process and then allowed to cool down gradually. This cooling relieves any internal stresses on the glass. You'll notice when the annealed glass breaks, not only is the cracking slow, but sometimes it doesn't even make it to the other side of the glass, which is good for windshields. A small crack in one spot of the windshield doesn't completely blind your vision. Also, they put a piece of plastic in between 2 sheets of annealed glass so that these big shards don't fall in and cut you inside the car. Tempered glass is very different. Instead of allowing the glass to cool down slowly, they use forced air to cool down the outer sides of the glass really quickly, which leaves the inside of the glass hot. Kind of like how a Prince Rupert's drop is made if you remember that video. The inside is still hot, so as it cools down, it shrinks and pulls in, which puts the outside of the glass in compression, but the inside in really high tension. Just like the Prince Rupert's drop, if you can get through that hard outer layer, it releases the tension and the failure front destroys the entire sheet of glass. On the Prince Rupert's drop, you have to get through the outside curved surface of the drop to release the tension. But on a car window, you have to get through the flat tempered surface to release the tension. With a sheet of glass, though, we have to start it along one of the edges. Even after you break tempered glass, you can sometimes still hear the stress releasing itself as it continues to break. So there you go. The next time you need to escape from a car window, remember that the windshield is annealed and it's going to hold together. But the side windows are tempered and they're going to bust out completely as long as you hit them on the edge. Okay, I'm just going to go for this. You're smart. You know how YouTube works. A company approaches a person with a large channel and says, can we sponsor a product on your channel? And the guy says, yes, and they agree on a price. This is different. I actually contacted this company because their product has changed my family.
All right. Now we're going to watch the Prince Rupert because it's cool too. So one more video and then we're done with this lesson.
Hey, it's me, Destin. Welcome back to Smarter Every Day. Today we're going to do awesome science with Orbix hot glass here at Lookout Mountain, Alabama. Goggle up. Science is about to happen. We're going to use a high-speed camera and learn about Prince Rupert's drop. It's never been done on the internet. You're going to learn something. Let's go. Okay, we are here inside the shop with Cal. Cal owns the place. Can you show me how to make a Prince Rupert's drop? Sure. We're going to gather some glass, drop it in a bucket of cold water. Cold water. So after it cools down, this is what you're left with. It kind of looks like a tadpole, but it has some really interesting mechanical properties. We can actually hit this thing with a hammer and it won't break. Okay, I'm ready. Didn't go. Okay, I think Cal is kind of a pansy, so you think you can break it? So we're going to try again, only this time I'm going to make you hit it really hard, and I'm going to record it with high speed. Does that work? Think you can break it? All right, let's do it. The challenge is on. I can just hit it? Yeah. Oh! So do you think you actually broke it? I don't think you did. You think you broke it? I know I broke it. Let's look at the high speed. Okay, so the drop broke, but technically it wasn't the hammer that broke it. If you look close in the high speed, you can see that it's the wiggling of the tail that makes it go. This is the mystery of the Prince Rupert's drop. You can try as hard as you can to break the bulb, but you can't. But if you even nick the tail, the entire thing will explode. Not shatter, but actually explode. Let's go outside and I'll show you more. Okay, we're going to just run an obscene frame rate here. We have this Phantom V1610. So glass breaking occurs so fast that you have to have like hundreds of thousands of frames per second. So we're going to have a lower resolution, and we have to have a lot of light as well. We're also going to use this Miro over here to run about 3,000 frames per second so we can get a wide shot to see the whole event as well. 3, 2, 1, go. Okay, now we understand what a Prince Rupert drop does, but at this point we don't quite understand why it does it. Let's take a closer look. Okay, this is called a polariscope, and basically what it is it's a filtered piece of glass that's polarized. Now I have another filter here. You can see if I turn it, then I can block out the light. Now if I put this on the camera that you're looking through here, and then I put the Prince Rupert's drop in between the two pieces of glass, you should be able to see the internal stresses built up inside the Prince Rupert's drop. So to understand how these stresses got here, let's use the color gray to represent nice and strong solid glass. We'll use red to represent molten glass, and because of the thermal expansion coefficient, it's safe to assume that the higher the temperature, the larger this glass wants to be. Blue represents glass that's cooling off, or transitioning between the two states. Because of that same thermal expansion coefficient, this glass is shrinking and basically pulling in on itself. Think of a Prince Rupert's drop as a bunch of little infinitesimal pieces of glass, with each piece trying to interact with the pieces around it. When the molten glass is first stripped into the water, the outside layer touches the water and immediately solidifies. This locks in that outside shape of the drop. The inside of the drop, however, is still a hot expanded liquid. As heat's transferred to the water, that glass on the inside slowly begins to cool down and pulls in against that outside layer. The problem is that because it's already locked in as a round solid, it only compresses tighter against itself. This actually makes it stronger, kind of like how an arch compresses and gets stronger when you put your weight on it, only this is in all directions. Now, because the cooling glass can't move that outside layer, it begins to pull against itself, causing it to be in extremely high tension. It then hardens in this state of tension, and there you have it, a Prince Rupert's drop. The outside is an extremely high compressive stress, and the inside is an extremely high tensile stress. If one link in this tension chain is ever cut, it breaks on down the line, feeding off of its own stored up energy, just like a chemical explosive does. The difference here is that instead of releasing chemical potential energy, mechanical strain energy is released. This wave of energy is what we call a failure front. You can directly measure the velocity of that failure front as long as you have a camera fast enough. Let's give it a shot at 130,000 frames per second. 3, 2, 1, go. Got it? So big thanks to Cal from Orbix Hot Glass. If you found this interesting and you want to support him by buying stuff, go click on the link wherever I put it and go check out his website. Click the cat to subscribe with the helmet. It's a sad looking cat. You've never caught the cat on fire, ever. Never. Not even once. Never. These things are named for a guy named Prince Rupert, imagine that, who lived in Bavaria back in the 1600s. Here. He brought these over as a gift to King Charles II in England, who gave them to his Royal Society to try to figure out. Yep, ready. Whoa, smokes. Tension's killing me. You know it blowed up. Yep, it blowed up.